Alright, so skill 4 short and sweet. The only two new formulas that you need to know are right here. Just a reminder, if they're asking for average kinetic energy or speed, that's going to be U. 3RT, the R is the 8.314 because it deals with joules. And molar mass is on the bottom. Molar mass has to be in kilograms. Over here, this is when we have to compare rate of effusions for different gases. So rate of the first gas over the second equals molar mass over the second over the first, and then square root it. So these are the only two new formulas we'll be using in skill 4. You don't need to use a formula for every problem. Some of them you can just reason out. So let's go ahead and take a look at the first one. Which of these gases contains atoms with the slowest average speed? So if it's asking about speed, you should be thinking of this formula. These variables will affect speed, okay? So 3 is always the same, R is always the same. So the two things that are going to affect speed are temperature and molar mass. So what kind of temperature would we want on top to get a bigger speed? So hopefully you're thinking a high temp, right? And this is for a fast speed, just so that we're straight. Right, a bigger speed. What type of molar mass would we need to get a bigger speed? Hopefully you're thinking small, right? But this question is asking for slowest. So if we want the slowest one, we want the lowest temperature, and we want the biggest molar mass. Now, if your heart desires, feel free. You can plug in temperature and molar mass in kilograms for all of these, and then see which one gives you the lowest U. You can do that and justify it mathematically. I'm just going to go through, and since I'm looking for a slow speed, first I'm going to look for a really, really low temperature. So I'm going to go ahead and get rid of A. And then I'm going to look at, these are all 300 and 250. So now I'm going to look for a big molar mass. So the molar mass of this is around 16. Xenon is in the 100s, like 131. And then we have argon, which is around, if you find it on the periodic table, 39.9. And then C2H2, if you add it up, is a molar mass around 26. So the biggest molar mass that's sticking out to me is xenon, and it has the lowest temperature, so that's going to be our answer. All the other ones are out. Again, if you want to prove it to yourself mathematically, solve this for every single one. All right, going down to the next one. How many liters of carbon dioxide can form when we have a mixture of C2H4 and oxygen, and it's going through complete combustion? So we're making carbon dioxide. It doesn't say, but y'all should know combustion means water. Let's balance this thing. 2, 2, 4, 5, 6. Okay, so notice they gave us liters. They didn't give us moles or mass to plug in for a stoic problem. But in the notes, we said that if temperature and pressure are the same, then the volume of a gas relates to the molecules of a gas. So since they gave us volume, we can assume that this is all happening at the same temperature, pressure. We are going to just use coefficients to solve this. So we can plug in liters like they're moles into the chart as long as it's the same volume and temp. Sorry, not volume and temp, temp and pressure. Sure. So right here I'm going to put moles or liters, coefficient equivalent. Only true if same temperature and pressure. And since they're not saying that it's anything different, we'll go with it. So we have 35.4 liters of this. We have 4.7 liters of this. 3, 1. Hopefully it's evident that this is our limiting, but we'll plug in numbers. 1.5, 6, 7. And it wants to know how many liters of carbon dioxide. So we're just looking for this. So since this is our limiting, we move it over. and you get 3.133. And that's your answer. B. All right, so let's go to the next one. Looking for the gas with the fastest speed. So just like up here, we want a high temp, but a small molar mass. So I'm gonna go through and look for the highest temperature. And it does have the smallest molar mass. That was easy. But if you want, feel free to plug them in and solve it for yourself. Like if they're a little bit closer in values, maybe you would want to be safe than sorry. All right, so let's go to this one right here. We know the rate of effusion for methane is 4.1 liters per second, so that's how much gas can escape out of a hole into a vacuum. What's the rate of effusion for C2H2 for the same container at the same temperature and pressure? So if they're at the same temperature and pressure and then its rate of effusion, you should think of this formula. Because the 3 and R aren't involved in this formula, we can leave the molar masses in grams because grams over grams will cancel out. If you want to convert them in kilograms so that you just don't forget to do that when you're using this one, feel free to. I just want to point that out. So up to you. So rate of the first gas of effusion is 4.1. Okay. We're looking for rate of the second gas. All right, so molar mass of C2H2 should go on the top. It's 26. Molar mass of methane should go on the bottom. So let's go ahead and solve for R2. And when you do that, R2 equals 3.218 liters per second. If you can't get that, ask somebody around you to show you the algebra. Get this side and then you do 4.1 over this side. Rearrange it to solve for R2. All right, the next one, an unknown gas has a speed of this, so this time they're telling us speed. When the temperature is this in Kelvin, so that's good. What is the molar mass? So we should be thinking of this formula. Now, when you solve for molar mass, your answer will be in kilograms, so just make sure you recognize these are in grams, and so you'll have to convert over. So I'm going to plug in what I know. My dog's snoring in the background. R's 8.314. Temperature's 234. Let's solve for molar mass. All right. So, the first thing I would probably do is square both sides to get rid of that square root sign. I'll just put this here as I go through it. So then this equals all of this without the square root sign. Just for the algebra. Challenged. Alright, so then I would move molar mass over here, multiply this through, divide over, and then we can go from there. So 3 times 8.314 times 234 divided by that answer. Okay, so molar mass equals 0.02018 kilograms. So if you want to get it to grams, 1 kilogram is 1,000 grams. Sometimes my dogs purr in their sleep, so 20.18 grams per mole. A. All right, 14. Calculate the temperature where RMS speed in a sample is this. So this is U. So U equals 3 RT over molar mass. All right, so we know it's xenon, so we know molar mass. Xenon's molar mass is 131.3 grams. Make sure you convert it to kilograms. All right, so 228.1 equals the square root of 3 R T is what we're looking for. Kilograms on the bottom, 131.3. All right, so the first thing I would do again is square both sides. So I'm just going to show my work down here. Now I'm going to start moving it over to isolate T. Temperature is 273.9 Kelvin. Okay. All right. And there you go. They're sleeping right there.